Hi everyone. In this lecture, I thought I'll very briefly mention about the intrinsic gains of MOS versus a BJT amplifier, common emitter and common source amplifiers. So, what is the maximum gain that you can get out of a single stage common source or or a common emitter amplifier? So, in a bipolar junction transistor, the collector current or the emitter current has an exponential dependence upon the input voltage that you apply. Okay, so therefore, so your IE, or I can write IC approximately as IS e power VBE by VT. This is in fact IE. So IC is actually alpha times IE, and so if I want to find the change in the collector current by IC, so in a common emitter configuration, the output current in a common emitter configuration I naught is nothing but the small signal collector current itself. So I am interested in finding dou IC by dou Vi, which is the transconductance of the BJT amplifier, can be very easily shown to be ICQ upon Vt, where Vt is the thermal voltage, which is approximately 25.9 millivolts at 300 Kelvin. Okay, so here the GM is actually linearly dependent upon the collector current. The maximum intrinsic gain of a common emitter configuration is simply GM into R naught, and R naught for a BJT depends upon the early voltage VA and the collector current. Again, this is a very well known point that if I vary the collector emitter voltage VCE and plot it and plot the collector current for a given quiescent base emitter voltage, you are supposed to, after once the device is in active region of operation, the current is supposed to remain constant, but in reality it would actually increase slightly, and this is because of a phenomenon called base width modulation. Again, any standard devices textbook will tell you that what it is. Okay, and we can extrapolate the point where it intersects. The magnitude of that point is called the early voltage VA, and R naught is defined as the slope of this line. Okay, and for a given collector quiescent current, we can define what is the R naught value for it. Okay, so we know that when you are going to treat, use this common emitter configuration as an amplifier, you are obviously going to use it in the collector region, and the slope is going to be constant throughout this region. It's assuming it's increasing linearly. So from that we can say what R naught is. Now once you know R naught, the product of GM into R naught is simply ICQ upon VT into VA upon ICQ. So therefore you get VA by VT as the intrinsic gain. Now the intrinsic gain here, if you look at the intrinsic gain, it is independent of current. It doesn't depend upon the quiescent collector current, but rather it depends upon the early voltage and the thermal voltage. This is your intrinsic gain A naught. So what do I mean by intrinsic gain is that this is the maximum gain you can get using a common emitter amplifier. You cannot get a gain more than this, a single stage common emitter amplifier. Similarly, I will try to find what is the maximum gain of a common source configuration. So we are assuming that these devices are somehow biased, and we are just trying to find the biased with some, here it's quiescent drain current. Okay, I have not shown the biasing arrangement. They are somehow biased, and we are trying to find the maximum intrinsic gain of these amplifiers. In fact, I'm not even drawing these small signal models. This is I'm assuming it's you know that already. So the intrinsic gain here is again minus GMR naught. Okay, I didn't write the sign here explicitly. In a common emitter configuration, the gain is negative. I've just written the magnitude of the gain, which is VA by VT. Now GMR naught is the intrinsic gain in a common source configuration as well. However, we know that the drain current of a MOSFET has a square law dependence on the gate voltage. Okay, in this case I've written beta n here. Beta n is nothing but mu n Cox W by L. So that's your beta n. I'm just calling it as beta n. So from this, if you want to find dou I naught by dou Vi, now that's nothing but the drain current, change in the drain current due to a change in the gate to source voltage. So that will be dou IDQ by dou VGS. So from that you would get beta n into VGS minus VTH. Okay. This can also be written as square root of 2i. Okay. 2i, this is GM, so I am writing it as 2i mu n Cox W by L. Okay, so here all I did was I just found what is VGS minus VT, which is 2 IDQ upon beta n in the square root. So if you, this is nothing, VGS minus VT can be written in terms of the drain current. I just substituted in this result and I get this expression. This is IDQ here, expression for GM. So here if you look at this expression, it tells you that GM depends upon the drain current and also the dimensions of the device. Unlike in a BJT, it didn't really depend upon the dimensions of the device, whereas here it has a dependence on the device dimensions as well. And R naught in a BJT, in a MOSFET, depends upon 1 by lambda into the drain current. Again, for a MOSFET, we can similarly draw the ID versus VDS characteristics. And the graph would be something like this. Ideally, for any change in the VDS, the output should not change, but there will be a small change in the output current. Okay, and the slope of this is what we define as 1 by R naught here, or GDS. It's also written as GDS, which is 1 upon R naught. Okay, so that will be 1 by lambda IDQ. So now if I multiply GM into R naught, okay, I am going to call mu n Cox W by L as beta. So you are going to get root of 2 IDQ beta n. For an NMOS it is beta n, 1 by lambda IDQ. So this gives me a result which is 2 by 2 beta n by lambda square IDQ. So here the intrinsic gain of a MOSFET in saturation region is actually inversely proportional to the quiescent drain current. Okay, so this tells us the intrinsic gain is actually inversely proportional to the square root of the quiescent drain current. So as per this equation, since beta n is nothing but mu n Cox W by L, if I keep increasing W by L, as I keep increasing the ratio of W by L, if let's say I make W by L infinity, this equation tells us that A naught will tend to infinity. You know, if W by L tends to infinity, then this tells us that A naught will tend to infinity. But in reality, that will not happen. Now, why is that? Why is that? That's because this square law relationship between the drain current and the VGS and the overdrive voltage, okay, I'm going to write VGS minus VT as the overdrive voltage. It's beta n by 2 into V overdrive square. This is valid only when the channel that is formed in a MOSFET is under strong inversion. Okay, so your gate voltage is sufficiently strong enough to completely invert the channel, then this relationship is valid. Now, for a finite drain current, if I'm making beta n infinity, if I'm making W by L infinity, I'm just making beta n infinity, then V overdrive will become negligibly small, which means your VGS will very closely approach the threshold voltage of the MOSFET. As your VGS approaches the threshold voltage of the MOSFET, the device enters subthreshold region. The device is no longer in the strong inversion region or the saturation region. In fact, it will enter a region called the subthreshold region. When the device enters subthreshold region, we will no longer have the square law equations. Okay. Now, when the device enters subthreshold region, the relationship actually strangely becomes exponential. So, I'll give an empirical expression. Any exponential device, the GM is going to be proportional to the quiescent current. So, I'll write an empirical result which is I drain upon 2 VT. So this is a result we use it. Empirical result that we use for analyzing circuits. Okay, and sometimes we actually run actual simulations on different technology nodes and find out the maximum GM. So essentially, what we do is we fix the drain current and we keep on increasing the width As you keep increasing the width, the GM saturates, the transconductance saturates, it doesn't increase after a certain point. Okay, we keep on increasing the W by L ratio, and after a point the transconductance remains constant, it doesn't change much. That value will be the fundamental limit for a given drain current. Now that value will keep increasing as you keep increasing the drain current linearly. In fact, it will keep increasing linearly. Okay, for different values of this, your GM will keep increasing linearly. So I mean the same thing for a MOSFET. For a BJT, in fact, GM is assumed to be there is no device variation there. I mean, it's almost assumed to be proportional to the quiescent collector current always. But for a MOSFET, your GM is proportional to square root of the drain current. But once you keep increasing the width, eventually the GM will become proportional to the quiescent current. Also, you should know that when you compare a MOSFET versus a BJT, for a BJT, it has an exponential relationship between the input voltage, which is B base emitter voltage, and the emitter current or the collector current. Whereas the drain current versus the gate voltage, that's actually a square law characteristic. Since exponential is going to raise much faster compared to square law, the GM will always be more for a BJT. The transconductance GM is always going to be more for a bipolar junction transistor device. Okay, so now I'll compare the GM of a MOSFET, which is IDQ upon 2VT. VT is your thermal voltage now. Okay, this result tells us that, in fact, I can write it as approximately as 2 IDQ upon 4 VT. Now, why did I write it in this format is we are used to using the expression for the GM of a MOSFET in terms of the drain current and the overdrive voltage. So, if you compare this, it tells us that when your device overdrive voltage approximately reaches 4 VT, which is approximately 100 millivolts at 300 Kelvin, your device should nearly start entering the subthreshold regime. Again, this is just a rough empirical number. You have to find this exact value through simulations. The maximum GM has to be found through simulations. There are test setups to do that as well. Okay, so the maximum GM is limited, and then it behaves like a exponential device, and your GM will be proportional to the drain current. Now, if I try to compute the intrinsic gain for a MOSFET, it will be GM into R0. That would be IDQ upon 2 VT into 1 by lambda IDQ. So this would come out to be 1 by 2 lambda into VT. Now if you look at this number, this is independent of the drain current. Okay, so the intrinsic gain, this is like a fundamental limit which depends upon the device parameters and the temperature. It is actually independent of the bias current, both for this is for MOSFET, and for a BJT the intrinsic gain was VA upon VT. Now if you look at both the intrinsic gains, they are independent of the bias currents. Okay, so then for any given, what does this tell you is that you can get the same intrinsic gain for different values of currents. Okay, so then how does current get decided in any circuit design? If for example you start designing an amplifier, okay, the first thing is you might design an amplifier for a certain gain. Now both these equations tell us that for the maximum gain that you can get out of these amplifiers is independent of the bias current. Then where do I choose my bias current? How do I choose my bias current? So then there are several other parameters which will dictate the bias current. So for example, one of the parameters is noise. Okay, so noise will tell you if you want low input referred noise, then you have to choose a high bias current. So for example, I'll just take one small example. The input referred noise of a common source amplifier is 4 kT gamma by GM. I've considered only the thermal noise. Now if I want to have a low thermal noise, then GM has to be very high. So if there is a noise level, noise power, if there is a noise specification given, the input referred noise is specified, then that normally decides your bias current. For different bias currents, you can still get the same intrinsic gain. So that's what I'm trying to arrive at here. The next important point, once you know the bias current, once you know the intrinsic gain, is the bandwidth, the speed of an amplifier. So there are two things. One, what is the maximum gain you can get out of a single stage amplifier? And for how, for what will be the maximum frequency up to which this gain, you can get a good gain from the amplifier. Okay, we know that all the amplifiers eventually, as you keep increasing the frequency, they'll encounter poles and then the gain would start rolling off. Okay, this A naught would eventually start rolling off and eventually at very high frequencies it would go to 0. Now what is the fundamental limit? To find that, what we will do is we will actually try to find Ft. Okay, Ft is the intrinsic gain, the intrinsic, the transit frequency or the maximum frequency for the operation of this device. There are two ways we can define Ft in. For a BJT, for example, I'll define it for a MOSFET. You can inject a current II and try to compute I naught, the output current, and then find the frequency at which the ratio of the current gains become equal to 1. Okay. See, for a MOSFET, the output current is always much greater than the input current because MOSFET doesn't draw any input current, an ideal MOSFET. So if the gain is becoming less than 1, then it's no longer behaving like an amplifier anymore. There is no power gain. Okay. Otherwise, you can also take a single MOSFET and drive another MOSFET with the same dimensions, with minimum dimensions. So you are just essentially what you are doing is you are just going to load this amplifier with a capacitance of CGS, approximately CGS, and trying to find the gain at this node, the first stage node. Now I'll try to find in both the approaches, and in both the cases I'm going to find A of S, the gain at this point, and then going to equate it to 1 and find the frequency at which it becomes equal to 1. Okay. Again, both of them tells us that the voltage gain, here this voltage gain becomes equal to 1. So after that, there is, your amplifier will no longer behave like an amplifier anymore. Okay, the voltage gain is going to become less than 1 after that frequency. So for the MOSFET, I am going to assume there is an input capacitance CGS. So the voltage, the VGS, the signal VGS is going to be II, I am drawing it for this circuit, I am writing it for this circuit, upon SCGS is VGS. And I naught, the output current I naught, small signal current, I am sorry, I used a small signal I naught, I am just using a different variable, I naught is just to say it's a small signal, will be GM into VGS, which will be GM II by SCGS. Okay. So now I am going to call this as beta of S, a frequency dependent current gain for a MOSFET, which is GM upon SCGS. Now this term beta upon SCGS, when it becomes equal to 1, and that occurs when your S equals, I'll just find the frequency it becomes equal to 1, and that will be omega equals GM by CGS. At this frequency, I'm going to call it the transit frequency, and Ft will be GM upon 2 pi CGS. Okay. So this transit frequency of this MOSFET is 1, after which the current gain of the MOSFET becomes less than 1. So essentially the MOSFET is no longer functional. I can say I can no longer use it as an amplifier. Similarly, for the voltage gain, I am applying a voltage which is VGS here. So the current flowing through this amplifier is I'm ignoring the sign. It is actually minus GM by SCGS. I'm ignoring the sign right now. I'm just interested in finding the magnitude of the gain becoming equal to 1. And you would get the same omega t as GM by CGS by this approach as well. Okay. After this, the gain of the amplifier is always going to be less than 1, both the voltage gain and the current gain. So there is no more of a power gain in this circuit. So for an amplifier, you need to have power gain, meaning the output power. So I am gone V naught, I naught is the output voltage and the output current should be always greater than VI, II. Okay. So when this ratio becomes less than 1, then it's no longer an amplifier, or equal to 1. Okay. Then so this is P naught by Pi. When it becomes equal to 1 or less than 1, it's no longer an amplifier. Okay. So Ft is generally high for BJTs compared to MOSFETs. So that is why BJTs still find applications in very high frequency circuits. Okay, if not purely as a standalone BJTs, if for gigahertz of application, sometimes we do go for BiCMOS technologies. Okay, a combination of both MOS and bipolar transistors. So that's all I wanted to discuss today about just the comparison between MOS versus BJT. Some important parameters. We said that the GM of a MOSFET is GM of a BJT is always greater than that of a MOSFET, and both for MOSFET and a BJT, the intrinsic gain A0 is independent of bias current. The maximum gain is independent of the bias current. For a drain, for a MOSFET it is IDQ, for a BJT it was ICQ. It was independent of both. Okay, and we also found FT for a MOSFET. FT for a MOSFET is the point where your amplifier no longer behaves like an amplifier, is the point where your power gain becomes less than 1 for a single MOSFET. So I'll stop at this point.